All right, so I'm going to talk about the functions that I've provided for you to use on your project simulating a distillation column. So first of all, if you go to the class Piazza page, at the bottom, on the Resources tab, at the bottom in General Resources, you'll find this zip file containing the functions that I've given you, the distillation functions. So download the zip file, unzip it, and in the folder that you unzip into, you will find these functions. So we have a bunch of the same stuff that we used for the bubble point calculation. We have this get k-values function. So that was the function that you used in your bubble point calculation. In addition, we've got this kvalue.m, pr.m, parsedatabase.m, listspecies.m, thermodatabase.txt. Those are all auxiliary programs that get k-values uses. All right, and those were all present when you did your bubble point routine. The new functions now are getStream enthalpy and find initial values. Find initial values is going to set up your column at the beginning, so it will set up an initial guess for temperature, pressure, vapor and liquid flow rates, and compositions. On the entire column, those are the initial guesses that you begin iterating on. GetStream enthalpy is a calculator for the enthalpy of a stream in the column, and it's actually set up so it can calculate the enthalpies of all the streams simultaneously. So detailed descriptions of the functions can be found in this PDF, distillationfunctions.pdf. I'm not going to go through it in detail now. You will download it and you can read it. Basically, I've described the input and the output of each of the functions. Okay, so let's begin by looking at getStream enthalpy. All right, so if you open... Okay, so let's begin by looking at find initial values. If you open the M file for find initial values, you'll see that in the comments at the header, we've got instructions for what we need to run this. And it looks kind of complicated, but everything here is pretty straightforward. So there are 1, 2, 3, 4, 5 outputs. These outputs are pressures at every stage, temperature at every stage, vapor phase flow rate at every stage, and liquid and vapor compositions at every stage. What we need to plug in to find initial values are the component numbers. So again, this is referencing the component database that you used with the get k-values function when you did the bubble point. It's the same component database. You're using the same component numbers. Liquid feed rates, vapor feed rates, feed pressures, feed temperatures, liquid phase side stream flow rates, vapor phase side stream flow rates, the identity of the light key, the pressure drop per stage, the flow rate of vapor leaving the condenser, and the reflux ratio. Okay, so given these inputs, you'll be able to generate initial guesses for all of these thermodynamic variables. Let's see how it works. All right, so the first thing we're going to want to do is we're going to want to make sure that we return all of these variables that we need. All right, so we're going to want to get a pressure, temperature, vapor phase flow rate, compositions. All right, we'll set this equal to the output of find initial values. Okay, what find initial values needs are the components, feed flow rates, feed pressures, feed temperatures. Okay, so these are all things that we should probably set up before we try to feed it in here. Okay, so let's just do a quick copy onto the command line so we have in front of us what we're going to need. Okay, we're going to need these. I'm just going to put that here. Error, but it doesn't matter. I just want this as reference. Okay, so components is going to be a vector containing all of the component numbers. So let's do all 6 components, or the first 6 components. 1, 2, 3, 4, 5, 6. And of course, square brackets. Okay. LF now is the liquid phase flow rates of each of the components. So the structure of LF is a matrix. It's going to be a matrix with n rows, where each row represents a stage, and c columns. where each column represents one of the components in our system. So what we're going to do is we're going to set up the feed flow rate for each component at each stage in this N by C matrix. All right, so let's say that we've got 10 stages on the column and a single feed stage at stage 5. So that means that my per component flow rates are going to be 0 for every component at every stage except at this fifth stage. So when I'm setting up the matrix, I can do it as follows. LF, so start with the first row. Sorry, LF is going to equal. So start with the first row. Right, the first row is going to be, again, for a column with 10 stages and feed at the fifth stage, the first row is going to be all zeros. We have 6 components, so we're going to need 6 zeros in this first row. Okay? Same thing for the next row. I'm using the ellipses notation here just to put everything on a different line so that it all stays clear. All right, so that's the first row, second row, third row, fourth row. The fifth row now I have a feed. So let's say I've got 10 kilomoles per hour of every component. The unit on LF is kilomoles per hour. So I'll do 10, 10, 10, 10, 10, 10. So a liquid phase flow rate of 10 kilomoles per hour for every component in the fifth stage. So that's where my feed is. All right, now the flow rate is going to be 0 for the remaining stages. So stage 6, 7, 8. Stage 9 and 10. Can close this matrix up now. And there's my liquid phase flow rate matrix. The vapor phase flow rate matrix has exactly the same structure. So each row represents one of the stages, the feed at one of the stages. Each column represents one of the components. And the order of these columns is the same as the order in which I've entered my component numbers in my component vector. Okay? So for VF, we're going to enter on every feed stage the flow rate of the components in that feed stage. So let's say that my VF was identical to my LF. I can just say VF equals LF, and now I've set that up too. All right, so I've got VF set up. Okay, PF and TF are the temperatures and pressures at each feed stage. So again, I'm going to have one of these defined for every stage on the column, but they're going to be 0 for every stage that's not a feed stage. All right, so these have dimensions of n by 1. So they're going to have n rows, 1 column, each row for one of the stages. So let's set up PF. Let's say that at my single feed stage, my fifth stage, I'm going to have a pressure of 300 kilopascals. So the units on PF are pascals, and each row is going to be 0 except for the fifth row. 1, 2, 3, 4. And the fifth row is 300 kilopascals. Then 5, 6, 7, 8, 9, 10. 10 rows. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I only want 10. All right, so that's the structure of PF. TF has exactly the same structure, except now it's temperature in Kelvin. So let's say I've got 310 Kelvin in the single feed stage. All right, so you can see now the structure of these variables defining the feed, right? LF and VF show flow rates in the liquid and vapor phase, respectively, of each of our 6 components at any stage entering in the feed. If I've only got one feed stage, I'm only going to have numbers for that stage. Right? I only have numbers at the feed stage. Everything else is 0. Same thing for PF and TF. I only define a pressure and a temperature at the feed stage. 0 doesn't mean I'm working at absolute 0 or 0 pressure. It means that there's no feed defined for that stage. Okay, so what's next? What's next is the liquid phase side stream flow rates at each stage, U. So let's say I don't have any side streams except for the distillate. I need to do a quick material balance based on what I think the result of my separation will be in order to figure out what the expected distillate flow rate is, but I can do that. So you should do that calculation, figure out an expected distillate flow rate, and then U1, the first element in this U vector, is going to be the distillate flow rate. We allow a side stream flow rate in the liquid phase to be defined for every stage, but if your only side stream is the distillate, then that flow rate will be 0 for every other stage. All right, this also is an n/1 vector, so U now has the structure. So let's say I expect half of the stuff to go up and half of it to go to the bottom, so I've got a total of 60 plus 60 is 120 kilomoles. If half of it goes to the top, we've got 60 kilomoles going to the top. So this side stream flow rate is going to be in kilomoles per hour. And then it's 0 for everything else. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 stages. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 stages. U is defined. W then is my vapor side stream flow rate. If there's no vapor side stream, then this is just going to be 0 for every stage. Okay. And then what else? I need to identify the light key. I need to say what the pressure drop is at every stage. I need to say what the vapor phase flow rate leaving the condenser is, and I need to say what the reflux ratio is. Okay, so I'll give you the light key. Let's say that the light key in this case is going to be component number 2. All right, so let's make the light key component number 2, and we'll set a pressure drop at. Let's make it 100 Pascal per tray. So let's do 0.1 kilopascal per tray. Let's say that there's no vapor leaving the condenser and a reflux ratio of 2.5. Okay, so we can do this whole thing. Let's just use the function prototype to copy what we're going to enter here. Go to the top. Okay, so I'm going to get pressure, temperature, vapor phase flow rate, X and Y. I've defined components, I've defined LF, I've defined VF, PF, TF, U, and W. I said the light key is going to be component number 2. Pressure drop is going to be 100 pascals per tray. We've got a total condenser, so there's no vapor leaving the condenser, and the reflux ratio is 2.5. And let's take a look at get stream enthalpy. Okay, so what do we need here? We've got pressure, temperature, component numbers, compositions, and phase, the phase of the stream. All right, so we can calculate for either vapor or liquid streams. So this is either a letter V or a letter L. Okay, so get stream enthalpy works for a single stream, or you can run it on a set of streams. The way it works is as follows. Okay, so let's do get stream enthalpy. Okay, so we'll need a pressure, temperature, component numbers. So same thing that we had before. Just make this our vector 1, 2, 3, 4, 5, 6. Compositions. Right? This can also be a vector showing the compositions in either the vapor or liquid phase for each of our 6 components. So let's just make this. Let's actually copy this and let's just take a look at X. Okay. All right, so let's use the compositions that we actually have in this X matrix at, say, this stage. All right, so we'll just copy and paste those compositions. And then what else do we need? For get stream enthalpy, we're going to need a phase. All right, so the last thing that goes in is a Let's do liquid. Here we turn, we get an enthalpy. All right. We could also do it if we were talking about a vapor stream. Now that's the enthalpy. That's the enthalpy for the vapor stream. Now stream enthalpy will also work if your inputs are vectors. So the way that it would work is you enter a vector that contains the pressure at every stream you're analyzing, the temperature at every stream you're analyzing. Components is just a list of components. So it's the same thing that would be in the case of analyzing a single stream. Compositions then becomes a matrix. It's going to be an n by c matrix where every row represents one of the streams that you're analyzing, and the columns are the components in that row. And V or L is going to be either vapor or liquid. You can only analyze a set of vapor streams or a set of liquid streams. You can't analyze vapor or liquid streams simultaneously. Okay, so how would this work? Well, we've got our pressures defined, right? Pressure is P. We've got our temperatures defined. Temperature is T. All right, so we already have those in vector format. We can also look at our X compositions. Those are all defined. So let's do get stream enthalpy with our pressures as defined, temperatures, component numbers is the same, 1, 2, 3, 4, 5, 6. Compositions now we'll just do X, and that's for the liquid phase. Here we turn, and we get a vector of stream enthalpies, one for every stream that we're looking at. So this is basically going to give us the enthalpy of the liquid streams leaving each stage. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 stream enthalpies, one for each stage. We could do the same thing for the vapor. So now we're looking at the vapor phase compositions, and we're telling it to do a vapor phase enthalpy. And we get the enthalpies of the vapor, and we're done. So we can get stream enthalpies for as many liquid or as many vapor phases as we want. The units of enthalpy here is going to be in joules per mole. So we got enthalpy in joules per mole. Okay, so that's what you got. Again, this distillation functions.pdf file gives you detailed instructions on how to use all of these. We'll take a closer look at these in class next time.